Hello everyone, in this recording we're going to discuss structured graphs. So what do I mean by a structured graph? I mean any kind of layout where you're not just using a very generic node link or adjacency matrix. You can often exploit information available in your data or in your task to come up with a layout that's a little bit more tailored to your need. So here's one example. So this is a visualization of all the relationships between people in royal families in Europe. So each node is a person, you can hover and you can see kind of the entire relational tree. And this is an example of a structured graph because rather than just using kind of a generic force layout diagram, they've laid out each of the royal houses as different columns. So each of these countries gets its own column. And you can see that there are relationships across the countries, but there's a very natural grouping. Right? So that wouldn't have been done if you were just using a naive force layout visualization. So let's see a kind of simpler example of this. So if I had just used straightforward force layout on this simplified example, there are kind of three obvious clusters, right? These three groups, but this one is kind of crossing over, and this one also kind of crosses over, and you think that there should be a little bit more natural separation between them, right? And you can actually enforce that by using a library called Cola. So this is what it would look like if I use the constraints in the Cola library. I can tell it, I want all the nodes in this group to be separate from all the nodes in this other group, right, so that I can easily see these three separate groupings. And so how do you actually implement something like that? You can use code that looks like this. It's very compatible with using D3. In fact, there's already this function called the Cola D3 adapter. So all the code that we've already run with D3 to do force layout diagrams, you can still use here, and it will just add on some additional constraints. Right? And it's really these two lines that are implementing this visualization. This constraints call is taking a bunch of objects that look like this, and is telling you between a pair of nodes, what constraints do you want it to have to satisfy? Right, so in this case, I've taken every pair of nodes between these two groups and said I always want the nodes in this group to lie to the left by at least this many pixels compared to the ones over here. And I've done the same kind of constraint for this pair, all the pairs here. Right, so I've defined those separation, and then it will do the layout respecting that separation. Right. I've also added this groups argument so that it's going to try to put them all in some kind of common space so that the groups don't overlap. Okay, so that's kind of the special case where you have clear clusters and you want those clusters not to overlap. A little bit more generally, you might have a whole hierarchy, right? So in this case, the nodes in the graph are actually just the bottom levels of this tree. So that's, if you were just looking at the ordinary node link diagram, it would just be these small blue circles. But you might know that small neighborhoods of the graph should be grouped, and maybe there's coarser groupings as well, in which case you get this whole tree. Right? You can often try to lay out the graph in a way that shows this grouping. We'll see actual example right below. But the idea applies not just to node link diagrams, you can also use it in adjacency matrices. The most natural thing to do is just draw a tree along both the rows and the columns that show how do the nodes along the rows of the adjacency and columns of the adjacency relate to one another in these groupings. Okay. So here's an example using Cola library again. Where is it? Here. Okay. So what's going on? There's a hierarchy. So there's this subgroup with C and B. There's another group with A. And kind of the nice thing is that it's always ensuring that the nodes between the groups don't overlap with one another. Right? It also, the grouping object makes it like our eyes naturally gravitate towards seeing what are the structure. Okay. Here's an example that doesn't even use the Cola library. All I've done is, this is the Les Miserables dataset. I've taken all the groups according to some color, and then I've just calculated the convex hull around that color. Right? Once I know that convex hull, I can draw a path along that boundary And then just every time the force simulation ticks, I update that boundary, and it creates this kind of illusion of an animated clumping of all the nodes, right? So a little bit more detail of that. I've written this convex hull function in the linked code, and it's just a very light wrapper of an existing function in D3 called polygon hull. You basically just give it all the XY coordinates of the points that you want the convex hull of, and it will figure out the coordinates for all the points along a boundary. And then you can just draw a path, right? The same way that we've been using line generators, path generators, you can just draw a path that contains that, or that goes along that boundary, and you can fill it in with the same color. And so here I've appended the paths, used a path generator that goes through that boundary, and I filled it in with the same color as all the nodes. Right? It doesn't do the nice kind of separation of the groups that you would get if you used Cola, but it does serve the purpose of grouping all the points visually. Okay, so there's another kind of very specific kind of clustering structure where I like this kind of visualization. The idea is that if you have very dense, tight clusters that are occasionally separated by like a few inter-cluster links, right? You kind of want to do something in between an adjacency matrix and a no-link visualization. The reason is that if you have really tight clusters, it's hard to tell kind of which pairs are actually linked to one another. Right? You get the impression that a lot of the pairs in that cluster are linked with one another, but you don't really get to see which is which connections really exist, right? For that kind of very detailed query, you kind of need to use an adjacency matrix, right? An adjacency matrix is very obvious to tell. Like if you saw something like this, you would know exactly, like, okay, this node has links across all of here. But there's also this one edge that you might not have noticed if it had just been a node link diagram, right? But if you made the entire thing an adjacency matrix, it would be a very inefficient use of space. Because, for example, from here to here, there's only 2 links, right? So you'd have this kind of huge block of space where you'd only have 2 filled in squares, right? So actually just making this huge adjacency matrix would have a lot of empty space, right? So the idea is find the densely connected clusters, draw the adjacency matrices for those densely connected clusters, and then use node link diagram to link the clusters to one another. Right? It's efficient because the node links, for these kind of sparse connections, node link diagrams are very efficient. Right? They don't have that much overlap. Okay, so I realize this is just a screenshot from some paper, but I hope you see this. You see that you could probably implement something like this in D3. Give yourself some time, right? We've already discussed how to build these adjacency matrices, right? So you could imagine drawing little group elements to contain each adjacency matrix, each one of these things, and then just use the same code from before. You would want to lay out the groups so that they respect these kind of edge relationships, right? But for that, you could just define a new point representing the entire adjacency matrix and run a force-directed simulation. And that would get the layout across each of these groups, right? And then you can draw the links using an SVG path. Okay, so even though it's not a non-trivial implementation, all the basic ingredients, we know how to make these kind of visualizations. Okay, so these are all relatively high-level properties of the graphs, the overall connectivity structure, but there are going to be a lot of tasks where the structure actually lies in the low-level information, right? So imagine you're trying to visualize some sort of social media data set. You probably don't really need to visualize the entire node link structure, especially if you want some sort of user-facing visualization, right? For a user-facing visualization, you might really care more about the neighborhood and the network right around the user, right? So this is often called ego network visualization. So just to illustrate, here's an example of a network where, here's the overall network, but then suppose you care about just showing the networks related to these 2 people, right? What you can do is you can take, this is the one person, here's the other person, and this is just drawing the 1st degree neighborhood, 2nd degree neighborhood, and then showing the relationships between friends across the two neighborhoods. Right? So you get a sense of how much overlap is there between these two individuals' eco networks. That can be a lot more informative to someone who's kind of trying to understand their local information compared to just trying to show the entire graph. And especially if you can make it interactive and allow people to kind of change the ecos and compare the ecos, this ends up being a very useful strategy. Okay, finally, dynamic graphs. So there could be an entire lecture just on dynamic graphs. There are quite a few different variations. Just wanted to show a couple ideas. So the first idea is you can do an animation, right? So this is a pretty natural idea. Our eyes very easily follow the change. You just have to make sure that the graph is not changing too much from one time step to the next, because if too many things change, it's really hard to follow. But other than that, it's actually a pretty intuitive strategy. People don't need to you don't need to write an explanation for how to read the graph. Right? Another kind of common strategy, you can do some sort of combined encoding, right? So here, each node is actually a little time series. And then you get to see the relationships across the nodes, and then you get a sense of maybe, similar on the same path, you might have similar kind of pattern or where the edges where things change a lot. Okay. And of course, you can always use faceting. Different facets correspond to different time points. Okay, so this has been kind of a bit more academic than most of our lectures, but I just want to give the idea that even though adjacency matrix and node link visualizations are very common, they are not by any means the only ways of visualizing graph data, especially if you have additional information that you would like to incorporate into your layout.